Close your eyes for a moment and imagine standing at the very edge of existence itself. Not at the edge of a cliff or the shore of an ocean, but at the absolute boundary of everything that has ever existed, everything that exists now, and everything that ever will exist. Now open your eyes and ask yourself the question that has haunted every civilization, every philosopher, every curious child who has ever looked up at the night sky and wondered, what is out there, beyond the farthest star, beyond the most distant galaxy, beyond the very fabric of space and time itself? This is not just a question. This is the question, the one that sits at the foundation of human wonder, the one that philosophers have debated for thousands of years, the one that keeps astrophysicists awake at night, scribbling equations on whiteboards, hoping to glimpse something, anything, that might hint at an answer. What exists outside the edge of the universe? Here is the uncomfortable truth that science has revealed. We do not know. But here is the exciting part. We have theories, wild, mind-bending, reality-shattering theories that suggest the answer might be stranger than anything our ancestors could have imagined. More universe, other universes. Infinite copies of you are reading these exact words at this exact moment. We cannot perceive, or perhaps the most unsettling possibility of all, absolutely nothing. Not space, not darkness. True nothingness is a concept so foreign to human experience that our brains struggle to even process it. Over the course of this journey, we are going to explore every possibility that science and human imagination have proposed. We will travel from the earliest creation myths of ancient civilizations to the cutting-edge theories of modern physics. We will examine bubble universes, brain cosmology, the multiverse, and the strange concept of false vacuums. We will ask whether space wraps around itself like the surface of a sphere, whether time itself has an edge, and whether intelligence from beyond our universe might already be watching us. But before we can understand what might exist beyond the edge of the universe, we need to understand something fundamental. We need to understand what we even mean when we say the word edge. When most people hear the phrase, the edge of the universe, they picture something like the edge of a table or the shore of a continent, a hard boundary where everything stops and something else begins. On this side, stars and galaxies and planets. On the other side, well, something else. A wall, perhaps, a void, another reality altogether. But cosmology, the science of the universe's structure and origin, tells us that the situation is far more complicated and far more fascinating than a simple boundary line. The universe, as far as we can measure, does not appear to have an edge in the traditional sense. There is no wall out there in space with a sign that reads, "End of universe, turn back now." There is no cliff where galaxies tumble off into oblivion. Space, according to our best measurements, appears to simply continue, and continue, and continue, perhaps forever. So when scientists talk about the edge of the universe, they are usually referring to something called the observable universe. This is the portion of the cosmos that we can actually see and study, the region from which light has had enough time to travel to Earth since the beginning of everything, roughly 13.8 billion years ago. Beyond this boundary, there is almost certainly more universe, more galaxies, more stars, more planets, but we cannot see them, not because our telescopes are not powerful enough, not because we lack the technology. We cannot see them because the light from those distant regions has not had enough time to reach us yet. The universe is simply too young. This is a profound idea, and it deserves a moment to sink in. The edge of our observable universe is not a wall in space, It is a wall in time. We are not limited by distance. We are limited by the age of the cosmos itself. Humans have always been obsessed with boundaries. Where does the land end and the sea begin? Where does the sky end and the heavens begin? Where does the known world end and the realm of monsters begin? Ancient maps often featured warnings at their margins. Here be dragons. The unknown was terrifying, but it was also irresistible. Something in the human spirit has always pushed us to venture beyond the edge, to see what lies on the other side of the horizon. The question of what exists beyond the universe is the ultimate expression of this ancient impulse. It is the final frontier, the last horizon, the one boundary that no ship, no spacecraft, no technology may ever allow us to cross. And yet, we ask the question anyway. We cannot help ourselves. It is part of what makes us human. But this question is not merely philosophical. It has real scientific implications. If there is more universe beyond what we can see, then our little patch of cosmos is just a tiny island in an unimaginably vast ocean. If there are other universes with different physical laws, then the very constants of nature that allow us to exist, the strength of gravity, the mass of the electron, the speed of light, might be nothing more than local accidents, random numbers that happen to allow stars and planets and life to emerge in our particular corner of reality. Understanding what lies beyond the edge could change everything we think we know about why we are here at all. Long before telescopes and satellites, humans looked up at the night sky and invented stories to explain what they saw. Every ancient civilization developed its own cosmology, its own map of the universe, its own answer to the question of where everything ends. The ancient Egyptians believed the sky was the body of a goddess named Nut, arched over the flat earth, her hands and feet touching the horizon at the four corners of the world. Each night, the sun god Ra would be swallowed by Nut's mouth in the west, travel through her star-speckled body, and be reborn from her womb in the east come morning. The edge of the world was defined by the goddess herself, beyond which lay only the primordial waters of chaos from which all creation had emerged. The Babylonians, those brilliant astronomers of ancient Mesopotamia, imagined the earth as a flat disk surrounded by a bitter, salt-filled cosmic ocean. Beyond the ocean rose mountains so tall that only gods and legendary heroes could traverse them. The Epic of Gilgamesh speaks of these boundary mountains, beyond which lies a realm accessible only to the divine. The edges of the world were dangerous places, populated by fantastic creatures and guarded by supernatural forces. The ancient Greeks transformed cosmology from mythology into something closer to science. By the 5th century before the Common Era, thinkers like Pythagoras and later Aristotle had concluded that the Earth was a sphere, suspended in space at the center of a much larger cosmic sphere. The universe was finite, bounded by a shell of fixed stars that marked the outermost limit of existence. Beyond that shell lay the realm of the divine, the empyrean heaven, where gods dwelt in eternal perfection. The universe had a definite edge, and that edge was the boundary between the mortal and the immortal, the physical and the spiritual. This geocentric model, refined over centuries by astronomers like Ptolemy in the 2nd century of the Common Era, dominated Western thought for more than 1,000 years. The Earth sat at the center. The moon, sun, and planets orbited in crystalline spheres around it. And at the outermost boundary, the sphere of fixed stars marked the edge of creation itself. It was a comforting model in many ways. The universe was finite. It had a center, and we were at it. It had an edge, and beyond that edge was God. Everything made sense. Everything had its place. Then came Copernicus, Galileo, and Newton. The Earth was dethroned from the center of the cosmos. The crystal spheres shattered. The stars were revealed to be other suns, impossibly distant, scattered through a universe far larger than anyone had imagined. And suddenly, the question of the edge became not just mysterious, but terrifying. If the universe were so much bigger than we thought, where did it end? Was there even an end at all? Today, thanks to centuries of observation and the astonishing power of modern telescopes, we have a remarkably precise understanding of the observable universe, the portion of reality that we can actually detect and study. The observable universe is a sphere roughly 93 billion light-years in diameter, centered on Earth. Not because Earth is special, but simply because we happen to be here, looking outward. Any observer, anywhere in the cosmos, would see their own observable universe, a sphere of the same size centered on their location. Now, you might be wondering how the observable universe can be 93 billion light-years wide if the universe is only 13.8 billion years old. After all, light travels at about 300,000 kilometers per second, the fastest speed at which anything can travel. If light has only had 13.8 billion years to reach us, should not the observable universe be only 13.8 billion light-years across? This is where things get strange. The answer lies in the expansion of space itself. Since the moment of the Big Bang, space has been stretching. Not into anything, mind you. Space is not expanding into some pre-existing void. Space itself is simply getting bigger. The distance between galaxies is increasing, not because the galaxies are flying apart through space, but because the fabric of space between them is growing. This means that light from distant objects has been traveling through an expanding medium. The galaxies that emitted that light 13 billion years ago were much closer to us back then, but during all those billions of years that their light was traveling toward us, space kept stretching. By the time that ancient light finally reaches our telescopes, the galaxies that sent it are now much, much farther away than they were when the light began its journey. The edge of the observable universe, the most distant point from which light has reached us, is currently about 46.5 billion light-years away in every direction. Double that, and you get the full diameter, 93 billion light-years. But here is the crucial point. The observable universe is not the entire universe. It is simply the region we can see. Beyond it, almost certainly, lies more. More space, more galaxies, more stars, regions of the cosmos that are forever hidden from us, not because they do not exist, but because their light has not yet had time to make the journey. Perhaps the most mind-bending aspect of the cosmic edge is that it is not really a location in space, it is a moment in time. When we look out at the most distant objects in the observable universe, we are looking back in time. Light from a galaxy 1 billion light-years away left that galaxy 1 billion years ago. Light from the edge of the observable universe left its source nearly 13.8 billion years ago, just a few 100,000 years after the Big Bang itself. The farthest thing we can see is not a galaxy or a star. It is the cosmic microwave background radiation, a faint glow of microwave light that fills the entire sky. This radiation was released when the universe was only about 380,000 years old, at a moment when the cosmos had cooled enough for atoms to form and light to travel freely for the first time. Before that moment, the universe was a hot, dense fog of particles, opaque to light. The cosmic microwave background is like a wall of light surrounding us in every direction, the oldest thing we can see, the baby picture of the cosmos itself. Beyond that wall, we cannot see. Not because there is nothing there, but because the universe before that moment was opaque. Our view is blocked, not by matter in space, but by conditions in time. So when we ask what lies beyond the edge of the universe, we are really asking two different questions. First, what lies beyond the edge of the observable universe, in those regions of space too far away for their light to have reached us? And second, what lies beyond the edge of time itself, before the Big Bang, before space and time, as we know them, even existed? Both questions lead us into territory where science blurs into philosophy, where hard data gives way to theory and speculation, where the brightest minds in physics debate possibilities that would have seemed like pure fantasy just a century ago. In the sections that follow, we will explore every major theory that science has proposed to answer the question of what exists beyond the edge. We will examine the theory of cosmic inflation, which suggests that the universe underwent a brief but unimaginably rapid expansion in its earliest moments. A growth spurt so extreme that it may have created a cosmos trillions of times larger than what we can observe. We will dive into the concept of eternal inflation and the bubble universe hypothesis, which proposes that our universe is just one bubble in an infinite cosmic foam, surrounded by countless other bubble universes, each with its own physical laws, its own history, its own possibility for life. We will investigate the shape of space itself. Is the universe flat, stretching out forever in all directions? Or does it curve back on itself like the surface of a sphere, finite but without any edge? We will explore the multiverse, the idea that our universe is just one of an infinite number of parallel universes, some nearly identical to our own, others unimaginably different. We will venture into the strange world of brain cosmology and string theory, which suggests that our entire universe might be a three-dimensional membrane floating in a higher dimensional space, alongside other membranes, other universes that we cannot perceive. We will confront the concept of true nothingness, the possibility that beyond our universe, there is no space or other realities, but the complete absence of anything at all. No space, no time, no energy, no matter. And we will ask the strangest question of all. Could there be intelligence out there, beyond the edge, watching us, perhaps even creating universes like our own? The journey will take us to the very limits of human knowledge and beyond, into realms where science meets philosophy, where mathematics meets imagination, where the known meets the unknowable. So take a deep breath, clear your mind, and prepare to venture beyond the edge of everything. The universe is waiting. Picture yourself floating alone in the middle of a vast, dark ocean at night. In every direction, the water stretches endlessly into blackness. Far in the distance, you can see a faint ring of twinkling lights, perhaps the glow of distant cities along some unseen shore. That ring of light is the only sign of civilization you can detect. You have no way of knowing how far those shores extend, what lies beyond them, or whether the ocean continues forever past that glimmering boundary. This is our situation in the cosmos. We are floating in an ocean of space so immense that the human mind recoils from truly comprehending it, and like that lone observer in the dark waters, we can only see so far. The ring of light we perceive is called the observable universe, and it represents everything humanity has ever seen, measured, or detected. Beyond that ring lies the great unknown. The observable universe is a sphere roughly 93 billion light-years in diameter. That number is so staggeringly large that it deserves a moment of contemplation. A single light year is the distance that light travels in 1 year, moving at about 300,000 kilometers per second. That works out to roughly 9.5 trillion kilometers. Now multiply that by 93 billion. The result is a number so vast that writing it out would fill pages with zeros. At the center of this sphere sits Earth, not because our planet is special or cosmically important, but simply because we are the ones doing the looking. Any observer, anywhere else in the universe, would see their own observable universe, a sphere of the same approximate size centered on their location. There is nothing unique about our vantage point. We are simply here, gazing outward at the portion of reality that light has had time to reveal to us. Now, you might be wondering about something. The universe is about 13.8 billion years old. Light is the fastest thing in existence, traveling at a fixed speed that nothing can exceed. So if light has only had 13.8 billion years to travel, why is the observable universe 93 billion light years across instead of 27.6 billion? The answer to this apparent paradox lies in one of the most remarkable features of our cosmos, the expansion of space itself. Since the moment of the Big Bang, space has been stretching, not expanding into anything, mind you. There is no pre-existing void that the universe is filling up. Rather, the fabric of space itself is growing. The distance between galaxies is increasing, not because the galaxies are flying apart through space like shrapnel from an explosion, but because the space between them is getting bigger. Think of dots painted on the surface of a balloon. As you blow air into the balloon, the surface expands. The dots do not move across the rubber. They stay in place. But the distance between them grows because the surface itself is stretching. This is what the universe is doing on a cosmic scale, and it has been doing it for 13.8 billion years. When light left a distant galaxy billions of years ago, that galaxy was much closer to us than it is now. The photons began their journey across a shorter gap, but as they traveled toward Earth, space kept stretching behind them and in front of them and all around them. By the time those ancient photons finally reach our telescopes, the galaxy that emitted them has been carried much farther away by the expansion of space. The light traveled 13.8 billion years, but the object that sent it is now 46.5 billion light years distant. Double that radius, and you get the full diameter of the observable universe, 93 billion light years. But here's the crucial point that changes everything about our understanding of reality. The observable universe is not the entire universe. It is simply the portion we can see. Beyond the boundary of the observable universe, there is almost certainly more. More space, more galaxies, more stars, more planets. Regions of the cosmos that exist but remain forever hidden from us because their light has not yet had time to make the journey to Earth. The edge of what we can see is not a wall in space, it is a wall in time. This boundary has a name. Cosmologists call it the particle horizon. It marks the maximum distance from which light could have traveled to reach us since the beginning of the universe. Everything inside the particle horizon is, in principle, detectable. Everything beyond it remains invisible, not because it does not exist, but because the universe is simply too young for light from those regions to have reached us. And there is something even stranger. We cannot actually see all the way to the particle horizon. There is another boundary closer to us, a kind of wall of light that blocks our view of anything more distant. This wall is called the cosmic microwave background, or CMB. It is the oldest light in the universe, released when the cosmos was only about 380,000 years old. Before that moment, the universe was so incredibly hot and dense that it existed as a glowing fog of particles. Photons could not travel freely. They bounced off the soup of electrons and protons that filled all of space, scattering chaotically in every direction. Then, something extraordinary happened. The universe cooled enough for atoms to form. Electrons combined with protons to make hydrogen. Suddenly, space became transparent for the first time. Light was free to travel unimpeded across the cosmos. That ancient light has been traveling ever since, and it now fills the entire sky in every direction as a faint glow of microwave radiation. When we observe the cosmic microwave background, we are looking at the universe as it appeared when it was less than 500,000 years old. We are seeing the baby picture of the cosmos itself, frozen in time and stretched to microwave wavelengths by billions of years of cosmic expansion. Beyond the CMB, we cannot see. The universe before that moment was opaque. Our view is blocked not by any physical object, but by the conditions that existed in the early cosmos. We have reached the ultimate limit of observation, a horizon set not by distance, but by the physics of time itself. But the cosmic horizon is not static. It is changing in two different ways that pull in opposite directions. On one hand, the observable universe is growing. Every second, light from slightly more distant regions reaches Earth for the first time. Our view of the cosmos is slowly expanding as ancient photons complete their long journeys to our telescopes. In a sense, we are constantly seeing new parts of the universe that were previously hidden from us. On the other hand, something troubling is happening. The expansion of the universe is accelerating. Driven by the mysterious force called dark energy, space is stretching faster and faster with each passing moment. This means that distant galaxies are receding from us at ever-increasing speeds. There is a boundary out there called the cosmic event horizon, beyond which galaxies are receding faster than the speed of light. Not because they are moving through space at superluminal velocities, which would be impossible, but because space itself is expanding so rapidly that it carries them away faster than light can travel. Every second, roughly 20,000 stars cross this event horizon and become permanently unreachable. The light they emit today will never, ever reach Earth. They are slipping beyond the boundary of knowability, lost to us for all eternity. In the distant future, as the cosmic expansion continues to accelerate, more and more galaxies will fade from view. Their light will stretch to longer and longer wavelengths, eventually becoming undetectable. Future astronomers, billions of years from now, will look up at a sky that appears nearly empty. They will see only the local group of galaxies, gravitationally bound together. They will have no evidence that trillions of other galaxies once filled the heavens. They will look out at the edge of their observable universe and see nothing but darkness. And they will have no way of knowing how much they are missing. This is perhaps the most unsettling implication of modern cosmology. The universe we can see is already just a tiny fraction of the whole, and that fraction is shrinking. We live in a brief cosmic moment when the evidence of the universe's true vastness is still visible to us. Future generations will not be so fortunate. The observable universe contains roughly 2 trillion galaxies, each hosting hundreds of billions of stars. The total number of stars in the observable universe is staggering, approximately 200 sextillion, a number written as 2 followed by 23 zeros. Each of those stars could potentially host planets. Each of those planets is a world unto itself, with its own geology, its own atmosphere, its own possibilities. And yet, all of this represents merely what we can see from our tiny vantage point. Consider what this means. Every photograph of deep space, every map of the cosmic web, every measurement of distant galaxies represents only the tiniest sample of what exists. The Hubble Deep Field, that famous image showing thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length, reveals only a fraction of reality. The actual universe extends far beyond, containing wonders we will never witness, structures we will never map, phenomena we will never understand. Some cosmologists estimate that the entire universe could be at least 250 times larger than the observable portion. Others suggest it might be genuinely infinite. If the universe truly extends without limit, then it contains not just more galaxies, but infinite galaxies, not just more stars, but infinite stars, not just more planets, but infinite worlds where every possible configuration of matter has been realized. In such a cosmos, somewhere unimaginably far away, there would be regions of space identical to our own. Another Milky Way, another solar system, another Earth, another civilization asking the same questions we are asking right now. So what lies beyond the observable universe? Almost certainly, more of the same. More galaxies forming and dying, more stars burning through their nuclear fuel, more planets orbiting in the cold depths of space. The laws of physics should be the same out there. The patterns of structure should be similar. It is simply more universe, extending outward in all directions, perhaps to infinity. We are like that observer floating in the ocean at night, surrounded by a ring of distant lights. Beyond the lights, we know there is more ocean. We simply cannot see it, and we never will. The Big Bang Theory stands as one of the great triumphs of human intellect. It tells a story of cosmic proportions, that our universe began 13.8 billion years ago in an unimaginably hot, dense state, and has been expanding and cooling ever since. The theory explains the cosmic microwave background radiation that fills all of space. It predicts the abundances of light elements like hydrogen, helium, and lithium with remarkable precision. It accounts for the large-scale structure of galaxies and galaxy clusters that we observe scattered across the heavens. But the Big Bang Theory, in its original form, had problems, puzzles that it could not explain. Mysteries that seem to require either astonishing coincidences or something fundamental missing from our understanding of the early universe. One of these puzzles was called the horizon problem. When scientists examined the cosmic microwave background, they found something remarkable and deeply troubling. The CMB has almost exactly the same temperature in every direction we look. The variations are tiny, about 1 part in 100,000. The universe appears to be in thermal equilibrium on the largest scales. But here is the problem. Opposite sides of the observable universe are so far apart that they should never have been able to communicate with each other. Light from one side has not had time to reach the other side since the Big Bang. So how did these distant regions know to be at the same temperature? It is as if two strangers on opposite sides of the planet who have never met, never spoken, and share no common history are wearing identical outfits. The coincidence seems impossible without some explanation. Another puzzle was called the flatness problem. Measurements tell us that the geometry of the universe is almost perfectly flat. Space does not curve noticeably on the largest scales. Parallel lines remain parallel. The angles of a cosmic triangle add up to exactly 180 degrees. But for the universe to be flat today, it had to be almost exactly flat at the very beginning. Even a tiny deviation from perfect flatness would have grown over billions of years, making the universe either drastically curved or collapsed back on itself long ago. the initial conditions had to be fine-tuned to an absurd degree of precision. A third puzzle involved magnetic monopoles. Certain theories of particle physics predicted that the early universe should have produced vast quantities of magnetic monopoles, hypothetical particles that carry only a north or south magnetic pole, never both. But despite decades of searching, not a single magnetic monopole has ever been detected. Where did they all go? In 1980, a young physicist named Alan Guth was working on these problems at the Stanford Linear Accelerator Center. He had been studying grand unified theories, which attempt to describe all the fundamental forces of nature within a single mathematical framework. And while wrestling with the monopole problem, he had a breakthrough that would transform cosmology forever. Guth realized that all three puzzles could be solved with a single elegant idea. What if the universe, in its earliest moments, underwent a period of incredibly rapid expansion? He called this idea inflation, borrowing the term from economics to describe the runaway growth of space in the primordial cosmos. According to inflationary theory, at a time between approximately 10 to the negative 36 seconds and 10 to the negative 32 seconds after the Big Bang, the universe expanded exponentially. During this unimaginably brief interval, shorter than a trillionth of a trillionth of a trillionth of a second, the universe grew by a factor of at least 10 to the 26th power. Some models suggest the expansion was even more extreme, perhaps by a factor of 10 to the 50th or even 10 to the 60th power. To grasp what this means, imagine a region of space smaller than a single proton. During inflation, that subatomic speck would have expanded to a size larger than the entire observable universe we see today. Distances doubled roughly every 10 to the negative 37 seconds. The expansion was so violent, so rapid, that it actually outpaced the speed of light. Not because anything was moving through space faster than light, which is impossible, but because space itself was stretching at a rate beyond comprehension. This solves the horizon problem beautifully. Before inflation, the entire observable universe was compressed into a region so small that all parts of it could easily communicate with each other. Light could travel from one side to the other. These regions had time to reach thermal equilibrium to settle into the same temperature. Then inflation took that tiny uniform region and stretched it to cosmic scales. The reason opposite sides of the sky have the same temperature is that they were once in intimate contact, long before inflation tore them apart. The flatness problem is also solved. Any initial curvature in the universe would have been stretched out by the enormous expansion. Imagine drawing a small circle on a balloon, then inflating that balloon to the size of the Earth. The curvature of the circle would become imperceptible. It would appear flat at any local scale. That is what inflation did to space itself. Even if the universe started with some curvature, by the time inflation ended, it would appear almost perfectly flat. And the magnetic monopoles? Inflation diluted them. If monopoles formed before inflation, the exponential expansion would have spread them so thin across such a vast volume of space that we would never expect to find one in our observable universe. They might exist out there somewhere, but they are so rare that detecting one is virtually impossible. Guth's original version of inflation had technical problems, but these were quickly resolved by other physicists. Andrei Linde in the Soviet Union and Andreas Albrecht with Paul Steinhardt in the United States independently developed an improved version called new inflation in 1981 and 1982. The theory was refined and strengthened, and it made specific, testable predictions. One of the most remarkable predictions was that quantum fluctuations, the tiny random variations in energy that exist at the smallest scales due to the uncertainty principle, would be stretched by inflation to cosmic sizes. These microscopic ripples in the quantum vacuum would become the seeds of all structure in the universe. The regions that were slightly denser than average would eventually collapse under gravity to form galaxies and galaxy clusters. The regions that were slightly less dense would become the vast cosmic voids. When scientists examined the cosmic microwave background with instruments like the COBE satellite in 1992, and later with the Wilkinson microwave anisotropy probe and the Planck satellite, they found exactly the pattern of fluctuations that inflation predicted. The tiny temperature variations in the CMB, the ripples in the oldest light, matched the theoretical predictions with stunning precision. The power spectrum, describing how fluctuations are distributed across different scales, fit the inflationary models almost perfectly. In 2002, Alan Guth, Andre Linde, and Paul Steinhardt shared the prestigious Dirac Prize for their development of inflationary cosmology. In 2014, Guth, Linde, and Alexei Starobinsky received the Kavli Prize for pioneering the theory. Inflation has become one of the most well-supported ideas in modern cosmology. But what does inflation tell us about what lies beyond the observable universe? The implications are staggering. During inflation, space expanded by at least a factor of 10 to the 26th power. The observable universe, all 93 billion light-years of it, represents just a tiny, tiny fraction of the region that was inflated. Beyond our cosmic horizon, there should be vastly more space, more galaxies, more stars, more planets. How much more? The calculations are almost beyond comprehension. Some estimates suggest the actual universe could be at least 150 times larger in diameter than the observable universe. Other calculations, using different inflationary models, suggest it could be 10 to the 23rd times larger. Some models predict the universe might be genuinely infinite in extent. The measurements from WMAP and Planck tell us that the universe is flat to within the precision of our instruments. A flat universe, extending forever in all directions, would be infinite. It would contain infinite space, infinite galaxies, infinite stars, infinite planets, and infinite possibilities. This flatness is not an accident. It is one of the strongest pieces of evidence for inflation. The boomerang experiment, flying high above Antarctica in balloons to escape atmospheric distortion, first precisely measured this flatness in the late 1990s. The WMAP satellite refined the measurement over years of observation, and the Planck satellite, with its exquisitely sensitive detectors, confirmed that the universe is flat to within 0.4%. These experiments measured tiny ripples in the cosmic microwave background, the afterglow of the Big Bang. The pattern of these ripples depends on the geometry of space. In a curved universe, the ripples would appear distorted, stretched or compressed, depending on whether space curves positively or negatively. In a flat universe, the ripples appear exactly as inflation predicts, and that is precisely what we observe. The scalar spectral index, a technical quantity that describes how the density fluctuations from inflation vary across different scales, has been measured with remarkable precision. The Planck satellite found a value of approximately 0.965, almost exactly what the simplest inflation models predict. This is not a coincidence. It is a fingerprint of inflation, preserved in the oldest light for 13.8 billion years. If inflation is correct, and all the evidence strongly suggests it is, then what we can see is nothing more than the tiniest drop in an ocean of unimaginable vastness. We are surrounded by more universe than we could explore in an eternity of lifetimes, separated from us only by the finite speed of light and the finite age of the cosmos. The story of cosmic inflation does not end with the rapid expansion of our universe. In many versions of the theory, inflation leads to something even more extraordinary, a cosmos that never stops inflating, continually spawning new universes in an endless process of cosmic creation. This idea is called eternal inflation, and it transforms our understanding of reality in ways that challenge the limits of human imagination. To understand eternal inflation, we need to think about what caused inflation in the first place. Physicists believe that inflation was driven by a special kind of energy field called the inflaton field. You can think of this field as an invisible substance that permeates all of space. When the inflaton field has high energy, it creates a kind of repulsive gravity that causes space to expand exponentially. When the field loses energy and settles into a lower state, inflation ends. The process of the inflaton field transitioning from high energy to low energy is called decay. But here is the crucial insight. This decay does not happen everywhere at once. It occurs randomly in localized patches of space. Picture a pot of water heated just past the boiling point. The water does not transform into steam all at the same instant. Instead, bubbles form at random locations, expand, and merge. Some regions are still liquid, while others have already become gas. The transition happens locally, not globally. Eternal inflation works in a remarkably similar way. In most of the inflating space, the inflaton field maintains its high energy, and inflation continues relentlessly. But in certain random locations, the field decays, inflation ends locally, and a bubble of normal, slowly expanding space forms. That bubble is a universe. Our universe, in this picture, is one such bubble. It formed when a patch of inflating space underwent the transition to a lower energy state about 13.8 billion years ago. Inside our bubble, the laws of physics as we know them took hold. Matter condensed from the energy released by the decay. Particles formed, atoms assembled, galaxies coalesced, stars ignited, planets accreted, and eventually, on at least one small world, life emerged and began asking questions about its own existence. But outside our bubble, in the regions where inflation never stopped, space continues to expand exponentially. And within that vast inflating background, new bubbles are constantly forming. Each bubble is a universe unto itself. The process never ends. It cannot end. As long as even a tiny fraction of space continues to inflate, new universes will keep appearing. The physicists who developed this picture include some of the most brilliant minds in theoretical cosmology. Paul Steinhardt, one of the original architects of inflationary theory, first demonstrated in 1983 that inflation could be eternal under certain conditions. Alexander Vilenkin at Tufts University showed that eternal inflation is actually a generic feature of most inflationary models, not a special case. Andrei Linde, working first in Moscow and later at Stanford, developed the theory of chaotic inflation, which naturally and inevitably leads to an eternally inflating multiverse. Alan Guth himself, the father of inflation, has stated that it is remarkably difficult to construct inflationary models that do not lead to eternal inflation. The multiverse, in his view, is not an optional philosophical speculation. It is an almost unavoidable consequence of the physics. Imagine the multiverse as a cosmic foam, endlessly bubbling with new universes. Each bubble expands into its own space, cooling and evolving according to its own internal physics. The bubbles are separated from one another by regions of still inflating space that grow faster than the bubbles themselves can expand. The bubbles can never catch up to each other. They are forever isolated, forever unreachable, like islands in an infinite ocean that grows faster than any ship could ever sail. But here is where things become even stranger. Each bubble universe might have different physical properties. The values of fundamental constants, the strength of gravity, the mass of the electron, the speed of light, all of these could vary from bubble to bubble. The decay of the inflaton field can happen in different ways, leading to different configurations of matter and energy, different particle species, different forces. Some bubble universes might have physics very similar to our own. Others might be radically different. In some, atoms might not be stable. Matter might not clump together. Stars might be impossible. These would be dark, sterile universes, devoid of structure, devoid of complexity, devoid of any possibility for observers. In other bubbles, the conditions might be even more favorable for life than in our own universe. Stars might burn longer. Heavy elements might be more abundant. The chemistry of life might emerge more easily. These could be universes teeming with intelligence, with civilizations far older and more advanced than humanity. Andrei Linde and his colleague Vitaly Vanchurin have estimated the number of possible universes in the eternal inflationary multiverse. Their calculations suggest there could be as many as 10 to the 10 to the 10 to the 7th power distinct universes, a number so enormous that it makes infinity seem almost comprehensible by comparison. But can we ever detect evidence of this multiverse? Can we peer beyond our bubble and glimpse the cosmic foam that supposedly surrounds us? Surprisingly, the answer might be yes. If bubble universes that form close enough together collide before the inflating space between them has time to push them apart, they would leave marks. A collision between universes would be a cosmic event of unimaginable violence, releasing enormous amounts of energy and creating a kind of shockwave that propagates through space. The signature of such a collision might be imprinted on the cosmic microwave background as a circular pattern, a disc-shaped region where the temperature is slightly different from the surrounding sky. And there is one intriguing anomaly that refuses to go away: the CMB cold spot. Located in the direction of the constellation Eridanus in the southern sky, the cold spot is a region about 5 degrees across that is significantly colder than the rest of the cosmic microwave background. It is roughly 70 microkelvin, colder than average, and it is unusually large compared to the typical fluctuations in the CMB. The probability of finding such a feature by chance, according to standard cosmological models, is only about 1 to 2%. One explanation is the Eridanus supervoid, a colossal empty region of space about 1.8 billion light-years across that lies in the direction of the cold spot. As light from the CMB passes through this void, it loses a small amount of energy, making that region appear colder. But detailed calculations suggest that even this enormous void can account for only about 20% of the observed temperature difference. This has led some physicists to propose a more exotic explanation. Laura Mersini-Houghton and others have argued that the cold spot could be the imprint of a collision with another universe, a cosmic bruise left over from a time when our bubble brushed against a neighboring one. The collision would have occurred in the distant past, during or shortly after inflation, and its signature would have been frozen into the CMB ever since. In 2011, a team led by Stephen Feeney published the first systematic observational tests of the bubble collision hypothesis in Physical Review Letters. They searched the WMAP data for circular patterns that might indicate past collisions. They found no definitive evidence, but they could not rule out the possibility either. The search for bubble collision signatures continues with ever more sensitive instruments. The Planck satellite provided higher resolution maps of the cosmic microwave background. Future experiments, including ground-based telescopes with even greater precision, will continue to look for the telltale circular patterns that would indicate our universe once collided with a neighbor. What would it mean if we found such evidence? It would be the first observational confirmation that our universe is not alone. It would transform the multiverse from a mathematical possibility into an empirical reality. It would tell us that the cosmic foam is real, that other bubbles exist, that the eternally inflating background continues to spawn new universes even now, and it would raise profound questions. If there are other universes, do they contain life? Are there observers in those distant bubbles, looking back toward us, wondering if we exist? The answers would remain forever beyond our reach, but the knowledge that we are not alone in the multiverse would change our understanding of existence itself. The implications of eternal inflation extend far beyond cosmology. They touch on the deepest questions of philosophy and meaning. If there are infinite universes, each with different properties, then in some sense every possibility is realized somewhere. Every configuration of matter that is physically possible exists in some bubble, in some corner of the eternally inflating cosmos. This is a strange new vision of reality. A cosmos not of one universe, but of infinite universes, eternally spawning new realities, forever beyond our reach, but perhaps forever shaping our understanding of what it means to exist. If such evidence is ever confirmed, it would be the first direct proof that other universes exist, not just theoretically, not just mathematically, but actually, physically, out there in the cosmic foam, separated from us by inflating space, but once close enough to touch. When we ask what lies beyond the edge of the universe, we are implicitly assuming something about the shape of space itself. We imagine that the universe has a form, a structure, a geometry. We picture it extending outward in all directions, perhaps forever, perhaps to some distant boundary. But what if the shape of the universe is stranger than we imagine? What if space curves back on itself in ways that make the very concept of an edge meaningless? To explore these possibilities, we need to understand two related but distinct concepts: geometry and topology. Geometry describes the local properties of space, how distances and angles work in your immediate neighborhood. If you draw a triangle on a surface and measure its angles, do they add up to 180 degrees, as they would on a flat table? Or do they add up to more, as they would on the surface of a sphere? Or less, as they would on a saddle-shaped surface? Topology, on the other hand, describes the global properties of space, how it is connected on the largest scales. A sphere and a donut have different topologies. You can stretch, bend, and deform a sphere in any way you like, but you cannot turn it into a donut without tearing a hole in it or gluing edges together. Topology is about those fundamental connectivity features that survive any amount of smooth deformation. Let us start with geometry. Based on everything we have measured with our most precise instruments, the universe appears to be flat. Not flat like a pancake with an edge, but flat in the mathematical sense of Euclidean geometry. Parallel lines remain parallel no matter how far you extend them. The angles of a triangle sum to exactly 180 degrees. Space does not curve on the largest scales. This flatness has been confirmed by multiple experiments spanning decades. The boomerang balloon experiment in 1999 and 2000, flying above Antarctica to escape atmospheric interference, made the first precise measurements of the acoustic peaks in the cosmic microwave background and found that the universe is flat to within a few percent. The Wilkinson microwave anisotropy probe refined this measurement to higher precision. The Planck satellite, with even more sensitive instruments, confirmed that the universe is flat to within about 0.4%. But here is the critical insight. A flat geometry tells you nothing about topology. A flat universe could be infinite, stretching forever in all directions, like an endless Euclidean plane. Or it could be finite, but without any boundary, wrapping around itself in higher dimensions like the surface of a torus. Think about the surface of a donut. If you were a tiny creature living on that surface, you would find that the geometry is mostly flat, at least locally. You could draw triangles whose angles sum to 180 degrees. You could send parallel lines in the same direction and they would stay parallel, at least for a while. But if you walked far enough in one direction, you would eventually come back to where you started. The surface is finite, yet it has no edge. There is no boundary you could reach, no wall you would encounter. You could walk forever and never find an end, yet the total surface area is limited. The universe could be the same way. Space could wrap around itself in 3 dimensions, creating a kind of cosmic hall of mirrors where traveling in a straight line long enough would bring you back to your starting point. If this is true, we might be able to detect it. The key lies in looking for repeated patterns in the cosmic microwave background. Imagine you are standing in a small room surrounded by mirrors on all sides, floor and ceiling included. You would see reflections of yourself stretching off in every direction, seemingly to infinity. But these are not real copies. They are images, illusions created by the geometry of the mirrors. If the universe has a compact topology, something similar could happen with galaxies and cosmic structures. Light from a distant object could reach us by multiple paths, some going the short way around and others taking the long way through the wrapped space. We might see the same galaxy appearing in different parts of the sky at different distances, showing us how it looked at different times in its history. Cosmologists have searched for these ghost images using a technique called cosmic crystallography, looking for correlations in the positions of distant objects that would reveal the repeating structure of wrapped space. They have also searched for matched circles in the cosmic microwave background, pairs of circles with identical temperature patterns that would indicate we are seeing the same surface from 2 different directions. So far, these searches have come up empty. No definitive evidence of a multiply-connected topology has been found. But this does not prove the universe is infinite. It only tells us that if the universe wraps around itself, it does so on scales larger than the observable universe. Some theorists have proposed specific shapes that might fit the data. The most famous is the Poincaré dodecahedral space, suggested by Jean-Pierre Luminet and colleagues in a paper published in Nature in 2003. In this model, the universe has the shape of a dodecahedron, a 12-sided solid made of pentagonal faces, but it is not a solid object floating in empty space. Rather, space itself has this shape. When you exit through one pentagonal face, you immediately re-enter through the opposite face, but rotated by 36 degrees. The universe is finite, with a volume about 120 times smaller than a simple spherical space of the same curvature, yet it has no boundary. You could travel forever and never reach an edge. The dodecahedral model was proposed to explain a puzzling feature of the cosmic microwave background, an unexpected lack of large-scale fluctuations. The CMB has plenty of temperature variations on small scales, but on the largest scales, the fluctuations appear suppressed. A finite dodecahedral universe would naturally explain this, because the largest possible wavelengths of fluctuation would be cut off by the finite size of space itself. Vibrations larger than the universe simply cannot exist. The Planck satellite data did not provide strong support for the Poincaré dodecahedral model, but they did not definitively rule it out either. The shape of the universe remains one of the great open questions in cosmology. Why does this matter for what exists beyond the edge? Because if the universe has a compact topology, there might not be any beyond. The universe could be all that exists. There would be no edge to cross, no boundary to breach, no outside to explore. Space would simply wrap around itself in a closed loop, finite in volume, but without any border. In such a universe, asking what lies beyond the edge would be like asking what lies north of the North Pole. The question assumes something that is not true about the geometry. There is no beyond because there is no edge. There is only the universe folded back upon itself, containing everything that is. Consider what it would mean to live in a wrapped universe. Light from distant galaxies could reach us by multiple paths, some going the short way around and others taking the long way through the folded space. We might see the same galaxy appearing in different parts of the sky, at different distances, showing us how it looked at different times in its history. The universe would be like a cosmic hall of mirrors, creating the illusion of infinity from finite space. If the universe is small enough and has the right topology, you might even see the back of your own head. Light leaving you would travel all the way around the cosmos and return to your eyes. Of course, given the size of the observable universe and the age of the cosmos, the image would be billions of years old. You would be looking at photons that left your location in the distant past, long before the Earth existed, long before the sun formed, perhaps even before our galaxy coalesced from clouds of primordial hydrogen. This might sound like science fiction, but it is a genuine scientific possibility that cosmologists have searched for by looking for identical patterns in opposite parts of the sky. The search has so far found nothing conclusive, which tells us that if the universe does wrap around, it must do so on scales larger than the observable universe. On the other hand, if the universe is flat and simply connected, as most evidence suggests, then it might extend infinitely in all directions. And an infinite universe is strange beyond imagination. It would contain not just more galaxies, but infinite galaxies. Not just more stars, but infinite stars. Not just more planets, but infinite planets. In an infinite universe, every possible arrangement of matter that does not violate the laws of physics must exist somewhere, given enough space. Every configuration is realized not just once, but an infinite number of times. Somewhere out there, inconceivably far away, there would be another region of space exactly like this one, another galaxy like the Milky Way, another solar system like ours, another Earth, another you. This is not mysticism or speculation. It is a logical consequence of infinity, combined with the finite number of possible particle configurations in any given volume. If space truly goes on forever, then duplication is not just possible. It is inevitable. The universe is vast enough to contain infinite copies of everything, including infinite copies of you. Reading these exact words at this exact moment in this exact order. The shape of the universe determines what kind of reality we inhabit, and we still do not know what that shape is. We have journeyed from the observable universe to the inflating cosmos beyond it, from bubble universes to the strange topology of space. But now we confront the grandest idea of all, the multiverse, the possibility that our universe, as unimaginably vast as it is, represents just one among countless others. The multiverse is not a single theory. It is a collection of ideas arising from different areas of physics, each proposing its own version of what other universes might be like and how they might relate to our own. The physicist Max Tegmark, one of the leading thinkers on this subject, has proposed a useful classification that divides multiverse theories into 4 distinct levels, each more radical than the last. The level 1 multiverse is the most conservative. It simply takes seriously the idea that the universe is infinite. If space extends forever and matter is distributed roughly evenly throughout, then there must be regions beyond our cosmic horizon that we can never observe. These regions are still part of our universe, governed by the same laws of physics. They are just too far away for light from them to have reached us. But in an infinite universe, every possible arrangement of particles must occur somewhere. Given enough space, every configuration allowed by physics will be realized not once, but an infinite number of times. This leads to a startling conclusion. Somewhere out there, fantastically far away, there are regions of space identical to our own. There are galaxies exactly like the Milky Way, solar systems exactly like ours, planets exactly like Earth, and people exactly like you and me. Tegmark has calculated how far away your nearest identical copy might be. The number is almost incomprehensibly large, roughly 10 to the 10 to the 29th power meters away. That is a distance so vast that writing it out would require more digits than there are atoms in the observable universe. But in an infinite cosmos, such distances are meaningless. Your doppelganger exists. In fact, infinite versions of you exist, living out every possible variation of your life. The level 2 multiverse is more radical. It is the multiverse predicted by eternal inflation, the theory we explored earlier. In this picture, our universe is a bubble that formed when a patch of inflating space underwent a transition to a lower energy state. Other bubbles are constantly forming throughout the eternally inflating background. Each bubble is a universe. The key difference from level 1 is that these bubble universes might have different physical constants. The strength of gravity, the masses of fundamental particles, the nature of the basic forces, all of these could vary from bubble to bubble. Some universes might have physics hospitable to life. Others might be sterile, incapable of producing stable atoms, unable to form stars or galaxies. The level 3 multiverse arises from quantum mechanics, specifically from the many worlds interpretation proposed by Hugh Everett in 1957. According to this interpretation, every time a quantum event has multiple possible outcomes, all outcomes actually occur, but in separate branches of reality. When a radioactive atom has a 50% chance of decaying in the next hour, standard quantum mechanics says it exists in a superposition of both states until observed. The many worlds interpretation says both outcomes happen. The universe splits. In one branch, the atom decays. In another, it does not. Both branches are equally real, and both versions of you continue to exist, unaware of each other. If many worlds is correct, then the universe is constantly branching into a vast tree of possibilities. Every quantum event, everywhere in the cosmos, creates new branches. The number of parallel realities would be beyond counting, each one as real as the one you experience right now. The level 4 multiverse is the strangest of all. Tegmark calls it the mathematical universe hypothesis. The idea is that every mathematically consistent structure exists as a physical reality somewhere. Our universe can be described by certain mathematical equations. The laws of physics, the properties of particles, the structure of space and time, All of these can be expressed in mathematical language, but there are infinitely many other possible mathematical systems, other sets of equations, other logical structures that are internally consistent. If all mathematically consistent structures exist physically, then there are universes out there governed by completely different mathematics, with completely different physics, with structures and entities we cannot even begin to imagine. Mathematics is not just a language we use to describe reality. Mathematics is reality, and all of mathematics is real. Brian Greene, another prominent physicist, has proposed his own classification, identifying 9 different types of multiverses arising from various areas of physics. His list includes the quilted multiverse of infinite space, the inflationary multiverse of bubble universes, the brane multiverse of string theory, the cyclic multiverse of colliding cosmic membranes, the landscape multiverse of string theory, vacuum states, the quantum multiverse of many worlds, the holographic multiverse, the simulated multiverse, and the ultimate multiverse that encompasses all possible realities. Why do physicists take these ideas seriously? Partly because they arise naturally from well-tested theories. Eternal inflation is a consequence of inflationary cosmology, which is supported by precise observations of the cosmic microwave background. The many worlds interpretation follows directly from the equations of quantum mechanics without adding any extra assumptions. The string theory landscape, with its vast number of possible vacuum states, emerges from the mathematics of the theory itself. But there is another reason the multiverse has captured attention. It might explain one of the deepest mysteries in physics. The laws of our universe appear to be exquisitely fine-tuned for the existence of complex structures and life. If the strength of gravity were slightly different, stars could not form. If the nuclear force were slightly stronger, all hydrogen would have fused into heavier elements in the early universe, and there would be no water, no organic chemistry, no life as we know it. If the cosmological constant were larger, the universe would have expanded so fast that galaxies could never have formed. If it were smaller or negative, the universe might have collapsed back on itself long ago. There are dozens of such coincidences, parameters, that seem set to precisely the values needed for a universe capable of producing observers. Why should this be? One answer combines the multiverse with the anthropic principle. If there are countless universes with different physical constants, then by definition we can only find ourselves in one where those constants permit our existence. The apparent fine-tuning is not a mystery. It is a selection effect. We are here because this is one of the rare universes where being here is possible. Not everyone is convinced. Critics like Paul Davies, George Ellis, and Sabine Hossenfelder have argued that the multiverse is not really science because it cannot be tested. If other universes are forever beyond our reach, if we can never observe them, interact with them, or gather evidence of their existence, then how can we claim they are real? The multiverse, these critics argue, is metaphysics dressed up in the language of physics. Supporters counter that the multiverse makes predictions, even if indirect ones. If eternal inflation is correct, we should see certain patterns in the cosmic microwave background. If the many worlds interpretation is correct, it makes exactly the same predictions as standard quantum mechanics for all experiments, and those predictions are confirmed daily in laboratories around the world. The multiverse may not be directly testable, but neither are many things we accept in physics, like the interiors of black holes or events before the Big Bang. The debate will likely continue for generations. The multiverse sits at the boundary between science and philosophy, between the testable and the theoretical, between what we can know and what we can only imagine. It forces us to confront deep questions about the nature of scientific inquiry itself. What counts as evidence? What makes a theory scientific? How far can we extend our theories beyond what we can directly observe? Some physicists argue that the multiverse is simply the logical endpoint of our best theories pushed to their natural conclusions. Just as accepting the spherical Earth led to the conclusion that there are places we cannot visit, accepting inflation leads to the conclusion that there are universes we cannot see. The mathematics points in that direction, whether we are comfortable following it or not. Others insist that science must remain grounded in observation, that theories which cannot be tested, even in principle, have crossed the line from physics into metaphysics. They worry that the multiverse represents a retreat from the rigor that has made science successful, a willingness to accept untestable explanations that would have been rejected in any other context. The debate continues. The multiverse remains one of the most controversial ideas in modern science, but it is also one of the most profound. If true, it means that everything we have ever seen, everything we have ever known, everything we have ever experienced, is just an infinitesimally small fraction of what exists. Beyond our universe lies not emptiness, not void, but an endless sea of other worlds, other possibilities, other forms of existence. What does it mean for us if the multiverse is real? Perhaps it diminishes our cosmic significance even further than Copernicus did when he removed Earth from the center of the solar system, or Hubble did when he showed our galaxy was just one among billions. In the multiverse, not only are we not at the center of anything, but our entire universe is just one bubble in an infinite foam. Or perhaps it expands the scope of existence beyond anything we previously imagined. If the multiverse is real, then reality itself is vaster than the vastest cosmos. Every possibility exists somewhere. Every story plays out. Every version of events occurs in some corner of the infinite. And somewhere out there, in a universe we will never visit, another version of you is contemplating the same question, wondering what lies beyond their own cosmic horizon, searching for meaning in the face of infinity. What if everything you have ever known, every galaxy, every star, every atom in your body, exists on a kind of cosmic sheet floating in a higher dimensional ocean? What if our entire universe is just a thin membrane, a surface stretched across dimensions we cannot see, and right next to us, separated by less than the width of an atom in a direction we cannot point to, lies another universe entirely? This is the strange and beautiful world of brain cosmology, and it may hold answers to some of the deepest mysteries in physics, including what lies beyond the edge of our universe. To understand brains, we must first understand strings. In the 1970s, physicists searching for a unified theory of everything discovered that if they imagined fundamental particles not as tiny points, but as vibrating strings of energy, the mathematics worked out in remarkable ways. Different vibrations would produce different particles, the way different vibrations of a guitar string produce different notes. But there was a catch. For the mathematics to remain consistent, string theory demanded extra dimensions. Not just the 3 dimensions of space and one of time that we experience, but 10 or even 11 dimensions in total. Where are these extra dimensions? We walk around every day, reaching out in every direction, and never bump into hidden dimensions. The traditional answer was that they must be curled up incredibly small, wrapped around themselves at scales far tinier than atoms, compactified into spaces so minuscule that no experiment could ever detect them. But in the late 1990s, physicists began exploring a radical alternative. What if some of these extra dimensions were not small at all? What if they were vast, perhaps even infinite, but we simply could not access them because we were stuck on a lower dimensional surface? This surface is what physicists call a brane, short for membrane. The term itself reveals the conceptual lineage. In string theory, branes can have different numbers of dimensions. A 0 brane is a point. A 1 brane is a string. A 2 brane is a sheet. And a 3 brane is a 3-dimensional volume, which is exactly what our observable universe appears to be. According to brane cosmology, our entire universe might be a 3-dimensional brane floating in a higher dimensional space called the bulk. Think of it this way. Imagine you are an ant living on a vast sheet of paper. You can move forward and backward, left and right, but you have no concept of up and down. For you, the paper is the entire universe. You could spend 1 billion years crawling across it and never suspect there might be more. Now imagine that paper is floating in a room with air all around it. The room is the bulk. Another sheet of paper might be floating just inches away, but you would never know it exists because you cannot move in the direction needed to reach it. This is the situation brane cosmology describes for us. We are like ants on a sheet of paper, unaware of the vast room around us or the other sheets floating nearby. In 1999, physicists Lisa Randall at Harvard and Raman Sundram at Johns Hopkins proposed 2 groundbreaking models that took this idea seriously. The first, called RS1, imagined our universe as one of 2 branes sitting at opposite ends of a 5th dimension. The space between these branes is warped, curved in a very specific way that has profound consequences for physics. The distance between the branes in the 5th dimension is not large by everyday standards, but the curvature of that dimension makes it effectively much bigger than it appears. The second model, RS2, went even further, proposing that our universe is a single brane floating in an infinite extra dimension. In this model, there is no second brane, no boundary to the 5th dimension. It stretches away forever. These models were not created just for mathematical elegance or theoretical play. They were designed to solve one of the most puzzling problems in physics, the hierarchy problem. Here is the puzzle. Gravity is extraordinarily weak compared to the other fundamental forces. The electromagnetic force that holds your atoms together is roughly 1 billion times stronger than the gravitational force between those same atoms. This disparity is so extreme that it cries out for explanation. Why? What makes gravity so feeble? In traditional physics, there is no good answer. The numbers just are what they are. But in the Randall-Sundram models, the answer is elegant and surprising. Gravity is not inherently weak. It only appears weak to us because it leaks into the extra dimension. While the other forces, electromagnetism and the strong and weak nuclear forces, are confined to our brane, trapped on our sheet of paper like an ant's feet, gravity can spread out into the bulk. It can travel into that 5th dimension we cannot access. Imagine trying to hear someone speak in a large empty warehouse versus a small sealed room. In the warehouse, the sound spreads out in all directions and becomes faint. In the small room, the sound is concentrated and loud. Gravity, spreading into the vast bulk, becomes similarly diluted. On our brane, we experience only a fraction of gravity's true strength. If we could somehow step off our brane and measure gravity in the bulk, it might be as strong as the other forces. This idea has startling implications that extend into experimental physics. If gravity leaks into extra dimensions, then the effects might be detectable at very short distances, or very high energies. Physicists at the Large Hadron Collider have searched for signatures of extra dimensions, looking for evidence of gravitons, the hypothetical particles that carry gravitational force, escaping into the bulk. These searches look for events where energy seems to disappear, carried away by particles we cannot detect because they have escaped into higher dimensions. In August 2016, experimental results excluded certain types of Randall-Sundrum gravitons with masses below about 4 TeV. So far, the searches have not found definitive evidence for extra dimensions, ruling out certain versions of these theories, but the hunt continues with each new experimental run. Now, here is where things become truly mind-bending. If our universe is a brain floating in the bulk, then what else might be floating out there? According to string theory, there could be other brains, other universes, drifting through the higher dimensional space. These parallel universes might be remarkably close to us in the extra dimension, perhaps separated by less than a millimeter, yet utterly unreachable because we cannot move in that direction. We are stuck on our brain the way characters in a painting are stuck on the canvas. Imagine 2 sheets of paper stacked on a desk, separated by a thin layer of air. Each sheet is a complete universe, with its own galaxies, its own stars, its own planets, perhaps its own forms of life. The inhabitants of one sheet might never know the other exists, even though, from a higher dimensional perspective, they are right next to each other. They could be separated by less than the width of a human hair in the extra dimension, yet more distant than any galaxy in the observable universe in any direction they can actually travel. This is the picture brain cosmology paints of the multiverse. But brains might not always remain separate. In 2001, physicists Paul Steinhardt at Princeton and Neil Turok, then at Cambridge, proposed one of the most dramatic cosmological scenarios ever conceived, the ekpyrotic model. The name comes from the ancient Greek word ekpyrosis, meaning conflagration, a term the Stoic philosophers used for the cosmic fire that periodically destroys and renews the universe. It is an ancient idea given modern mathematical form. In the ekpyrotic scenario, our Big Bang was not the beginning of everything. It was a collision. 2 brains, drifting through the bulk, approached each other over billions of years, drawn together by a force that acts through the extra dimension. As they came closer, their mutual attraction increased. When they finally touched, the impact released a colossal burst of energy. The kinetic energy of motion through the bulk was converted into the heat and matter of a newborn universe. This collision is what we call the Big Bang. The tremendous temperatures that filled our early universe, hot enough to forge protons and neutrons, came from 2 brains crashing together. If this is true, then our universe was born from a cosmic collision, and before the Big Bang, there was a previous universe, calm and nearly empty, slowly contracting as the brains drew closer. The Big Bang was not creation from nothing but transformation, a violent transition from one state to another. There was a before, even though it looked nothing like what came after. Steinhardt and Turok extended this idea into the cyclic model, which proposes that this process repeats eternally. After the Big Bang, the brains move apart, and the universe we know expands and cools. Galaxies form, stars ignite, planets coalesce. Dark energy eventually dominates, accelerating the expansion. The universe grows vast and cold and empty, but then, slowly, the brains begin approaching each other again. Their mutual attraction reasserts itself. Another collision occurs, another Big Bang, another universe filled with heat and light, and eventually new stars, new planets, perhaps new forms of life. This cycle might repeat forever, an eternal rhythm of creation and destruction with no ultimate beginning or end. The universe would be a phoenix, eternally dying and being reborn. The cyclic model makes testable predictions that distinguish it from standard inflationary cosmology. Unlike standard inflation, which generates strong gravitational waves in the early universe, ripples in space-time that would leave detectable patterns in the cosmic microwave background, the ekpyrotic scenario produces only very weak gravitational waves. The slow contraction phase before the collision does not amplify quantum fluctuations the way inflation does. If future experiments like CMB-S4 or the Simons Observatory detect strong primordial gravitational waves, it would be evidence against the cyclic model. If they find only weak ones, it would be a point in its favor. The model is not mere speculation. It makes predictions that can be tested. But can we ever interact with other brains? Could we send signals to a parallel universe floating nearby in the bulk? The answer, according to current physics, is almost certainly no. The forces that make up our existence, electromagnetism and the nuclear forces, are confined to our brain. We cannot reach across the bulk any more than characters drawn on a page can leap off the paper into the room where the artist sits. Gravity, however, might provide a faint connection. If gravitons can travel through the bulk, then gravitational effects from another brain might, in principle, influence our universe. Some physicists have speculated that dark matter, the invisible substance that seems to outweigh all visible matter in the universe by a factor of 5 to 1, might be ordinary matter on a nearby brain whose gravity we can feel, but whose light we can never see. The matter would be right there, in a sense, but forever invisible to our telescopes because light cannot travel through the bulk to reach us. This is speculative, of course. We have no direct evidence for extra dimensions or parallel brains. The Large Hadron Collider has not found gravitons disappearing into higher dimensions. No experiment has detected a fifth force leaking from the bulk. But the mathematics is compelling, and the ideas solve real problems in physics. Brain cosmology suggests that what lies beyond the edge of our universe might not be more space in the usual sense, but a direction we cannot point to, a dimension we cannot enter, where other universes float silently, forever out of reach. And perhaps, just perhaps, the Big Bang itself was not the beginning, but a moment of contact, a handshake across dimensions, a collision between worlds that gave birth to everything we know. If so, then beyond our universe lies not emptiness, but other realities, parallel sheets in a cosmic stack, each one a complete universe, each one utterly inaccessible, each one as real as our own. What is nothing? The question seems simple, almost childish, the kind of thing a 5-year-old might ask and an adult might dismiss. Nothing is the absence of something, the empty space, the void, the gap between things. But when physicists and philosophers grapple with this question seriously, probing its depths with mathematics and logic, they find that nothing is far stranger and more elusive than it first appears. And when we ask what lies beyond the edge of the universe, we must confront the possibility that the answer is nothing at all. But what kind of nothing? This is where the mystery deepens into something genuinely profound. In everyday life, when we empty a room of all its furniture, we say the room contains nothing. But of course, the room still contains air, billions of molecules bouncing around, carrying sound and temperature. It contains light, photons streaming through the windows. It contains perhaps dust motes drifting in sunbeams. Remove the air, pump it out with the most powerful vacuum equipment, and you still have something. You have space itself, the three-dimensional container in which things can exist. You have the electromagnetic field, ready to carry light even if no light is present. You have the gravitational field. Even the most perfect vacuum that laboratory equipment can create still contains something. It contains the vacuum itself, a substrate that permeates all of reality. Classical physics, the physics of Newton and the centuries that followed, imagined a vacuum as truly empty, a featureless void where nothing exists. Space was a stage on which the drama of matter and energy played out, but the stage itself was nothing, a mere emptiness, a geometric abstraction. But quantum mechanics shattered this picture in the 20th century. According to quantum field theory, the modern framework that combines quantum mechanics with special relativity, the vacuum is not empty at all. It seethes with activity. It is a roiling ocean of quantum fluctuations. Particles and antiparticles flicker in and out of existence, borrowing energy from the uncertainty principle and repaying it an instant later. These virtual particles are not directly observable in the usual sense. You cannot catch one in a detector and measure its properties, but their effects are measurable. They leave fingerprints on the real world. The most famous demonstration is the Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948 and confirmed experimentally by Steve Lamoureux in 1996. The setup is elegant. Place two uncharged metal plates extremely close together in a vacuum, just a few hundred nanometers apart. Classical physics predicts nothing should happen. There is no charge, no field, no force. The plates should simply sit there, indifferent to each other's presence. But quantum mechanics predicts otherwise. The vacuum between the plates can support fewer virtual particle fluctuations than the vacuum outside. Only fluctuations whose wavelengths fit an integer number of times between the plates can exist in that confined space. Outside the plates, all wavelengths are permitted. This creates an imbalance, a pressure difference. The vacuum outside pushes harder than the vacuum inside, and the plates are forced together by a tiny but measurable force. The Casimir effect proves that the vacuum is not nothing. It has properties. It has energy. It responds to boundaries. The empty space in which we exist is not empty. It is filled with quantum foam, a roiling sea of particle-antiparticle pairs, appearing and vanishing on timescales so short that we never see them directly but only feel their collective effects. The vacuum hums with potential. This quantum vacuum is sometimes called a false vacuum, particularly when physicists discuss the stability of our universe. To understand this deeply unsettling concept, imagine a ball resting in a valley. If the valley floor is the lowest point in the entire landscape, the ball is in a true vacuum state. It has nowhere lower to go. It is absolutely stable. But now imagine the ball resting in a smaller depression on the side of a mountain, a local dip that is not the lowest point overall. From the ball's perspective, it is in a valley, and it cannot easily escape. But a strong enough push, or a lucky quantum tunnel through the barrier, could knock the ball out of this depression and send it rolling down to the true valley floor below. This metastable state is a false vacuum. According to measurements of the Higgs boson and the top quark at the Large Hadron Collider, measurements of exquisite precision achieved through years of painstaking work, our universe might be in just such a state. The vacuum we inhabit appears to be metastable, a false vacuum rather than a true one. If this is correct, then somewhere in the landscape of possible energy states, there exists a lower energy configuration, a true vacuum with different properties, different physical constants, perhaps different laws of physics entirely. And here is the terrifying possibility. The transition from false vacuum to true vacuum could happen spontaneously. Somewhere in the universe, through a random quantum fluctuation, a tiny bubble of true vacuum could nucleate, like a bubble forming in a pot of superheated water. Once this bubble forms, it would expand at nearly the speed of light, converting everything it touches from false vacuum to true vacuum. The bubble wall would be a sphere of transformation sweeping outward at cosmic velocities. Inside this bubble, physics would be different. The masses of fundamental particles, the strengths of forces, the very fabric of reality would change. Atoms as we know them might not exist. The careful balance that allows protons and neutrons to form, that allows chemistry to happen, that allows stars to burn, and planets to form, and life to evolve, would be undone. The bubble would be a sphere of cosmic annihilation, erasing everything in its path, and replacing our universe with something fundamentally alien, something in which nothing we know could survive. Could this happen? In principle, yes, the mathematics allows it. But the calculations suggest the probability is extraordinarily low. The lifetime of our false vacuum, if it is false, appears to be far longer than the current age of the universe. Estimates suggest it might be stable for 10 to the power of 100 years or more, a number so large it defies comprehension. We are probably safe for longer than any meaningful timescale, but probably is not certainly, and the possibility remains, a sword of Damocles hanging over all existence. This brings us to an even stranger concept from the realm of string theory, the bubble of nothing. In certain solutions to the equations describing space-time with extra dimensions, a bubble can form that is not a region of different physics, but a region of literal nothingness. This is not a vacuum with quantum fluctuations. It is the absence of space itself. The boundary of the bubble is the edge of existence. Inside, there is no space, no time, no quantum fields, no anything, true nothingness. If such a bubble formed and expanded, it would not just kill us or change the laws of physics. It would unmake reality itself. Space and time would end at the bubble's boundary, and what lies inside is not describable because inside there is nothing to describe. There is no inside. The very concept of location becomes meaningless. The bubble of nothing is not a void. It is the end of voids, the end of emptiness, the end of anything that could be empty or full. Physicist Sidney Coleman, one of the great theorists of quantum field theory in the latter half of the 20th century, called vacuum decay the ultimate ecological catastrophe. If it happens, there is no warning, no escape, no recovery. The bubble expands at the speed of light, so we would never see it coming. No signal can outrun it. One moment existence, the next, void. The transition would be painless only because it would be instantaneous. But step back from this apocalyptic scenario and ask a more fundamental question. If our universe were to end, if all space and time ceased to exist, what would remain? Would there be a void, an emptiness, a nothing? Or is even the concept of remainder meaningless when there is no space in which anything could remain? This is where physics blurs into philosophy. The nothing that lies beyond the edge of the universe, if there is a beyond, might not be the nothing of empty space. It might be the nothing of non-existence, a state without space or time, without laws or matter, without even the potential for anything to exist. It is not black, because black is a color, and colors require light and eyes and space. It is not silent, because silence is an absence of sound, and sound requires air and ears and time. It is nothing at all. Some physicists have argued that this kind of nothing is unstable, that it cannot persist. Lawrence Krauss, in his controversial book, A Universe from Nothing, proposes that the laws of quantum mechanics might permit, even require, something to emerge from nothing. The vacuum fluctuations that create virtual particles might, under extreme conditions, produce real particles, real energy, even real universes. If this is true, then nothing, true nothing, might be impossible. Existence might be the default state, and the void might always give birth to something. Others are deeply skeptical. Philosopher David Albert and others have pointed out that if you start with quantum fields and their fluctuations, you are not starting with nothing. You are starting with something, namely quantum fields and the laws governing them. The rules of quantum mechanics are not nothing. They are something, a structure, a framework. True nothing would have no fields, no laws, no structure of any kind. And from that absolute absence, how could anything arise? What could cause it? This debate reaches to the heart of existence itself. When we ask what lies beyond the edge of the universe, one possible answer is nothing, a void, an absence, an end. But the more we probe the concept of nothing, the more elusive it becomes. Nothing seems to require something to be absent from. Emptiness seems to require a space to be empty. Perhaps beyond our universe there is not nothing but something else entirely, a different kind of existence we cannot imagine, structured by principles we have no access to. Perhaps nothing, true nothing, is a concept that does not correspond to any actual state of reality. Perhaps, as some philosophers have argued, the question why is there something rather than nothing is itself confused, based on assumptions that do not hold when pushed to their limits. What we can say with certainty is this: the vacuum is not empty. Space is not nothing. And even the most absolute void that physics can describe is filled with potential, with fluctuations, with the seeds of existence. Whether there is a nothing beyond this, a true nothing without even quantum foam, remains one of the deepest mysteries of cosmology and philosophy alike. And if our universe someday transitions to a true vacuum, if a bubble of destruction sweeps across the cosmos, or if existence itself somehow ends, what remains might be not darkness, not void, but simply nothing, a state beyond description, beyond thought, beyond being. The haunting possibility is that beyond the edge of the universe lies exactly that. Not more universe, not parallel worlds, not alternative physics, but the end of existence itself. True nothingness, waiting at the boundary of everything we know. When we speak of the edge of the universe, we instinctively imagine a boundary in space, a distant wall or horizon beyond which something else exists, something different, something other. Our minds reach for images of edges and borders, the familiar boundaries we encounter in everyday life: a wall, a cliff, the shore of an ocean. Somewhere out there, we imagine, the universe stops and something begins. But cosmology reveals a deeper truth that overturns this intuition entirely. The edge of the universe is not a place, it is a moment. The ultimate boundary is not spatial, but temporal. The edge of the universe is the edge of time. To understand this profound shift in perspective, consider how we observe the cosmos. Light travels at a finite speed, about 300,000 kilometers per second. When you look at the moon, you see it as it was about 1.3 seconds ago, the time it takes light to travel from there to here. When you look at the sun, you see it as it was 8 minutes ago. When you look at the nearest star system, Alpha Centauri, you see it as it was more than 4 years ago. And when you look at distant galaxies, you see them as they were millions or billions of years in the past. This means that looking outward into space is the same as looking backward in time. The farther you look, the older the light. Every telescope is a time machine, and the deeper it sees into space, the further it reaches into the past. This is not a metaphor or a poetic way of speaking. It is literal, physical reality. The most distant light we can see is the cosmic microwave background radiation, the afterglow of the Big Bang itself. This ancient radiation, detected first by Arno Penzias and Robert Wilson in 1965, has been traveling for 13.8 billion years. It shows us the universe as it was just 380,000 years after its birth, when the cosmos first became transparent to light. Before that moment, the universe was a dense, hot plasma of particles and radiation. Photons could not travel freely because they were constantly scattered by free electrons, bouncing around like light in a fog. Only when the universe cooled enough for electrons to combine with protons to form neutral hydrogen atoms could light finally escape. This moment is called recombination, and the cosmic microwave background is a snapshot of that era, a wall of ancient light surrounding us in every direction. It is the oldest thing we can see. It is the edge. We cannot see beyond this wall. Not because our telescopes are not good enough, not because we lack the technology, or the funding, or the ingenuity. We cannot see beyond because there is no light from earlier times. Before recombination, the universe was opaque. The cosmic microwave background is the edge of the visible universe, but it is an edge in time, not space. It is a when, not a where. So when we ask what lies beyond this edge, we are really asking, what happened before the oldest light? What existed in those first 380,000 years? And what, if anything, existed before time began? For the first fraction of a second after the Big Bang, conditions were inconceivably extreme. The entire observable universe was compressed into a space smaller than an atom. Temperatures exceeded anything we can recreate in laboratories by factors of billions. The four fundamental forces of nature may have been unified into a single force. Space and time themselves may have been different from what we know today, perhaps emerging from some more fundamental structure that we do not yet understand. Our current theories, even general relativity and quantum mechanics, break down under such extreme conditions. General relativity predicts a singularity at the beginning, a point of infinite density and curvature, where the equations give infinite answers and cease to make sense. Quantum mechanics, in its standard form, does not incorporate gravity at all. To truly understand what happened at the very beginning, we need a theory of quantum gravity, a framework that unites general relativity and quantum mechanics into a single, coherent description. We do not yet possess such a theory, though many physicists are working toward it. And what about before the Big Bang? This is where language itself starts to fail, where our everyday concepts of before and after become treacherous. In standard cosmology, the Big Bang was not an explosion in space, not a blast that occurred at some location in a pre-existing void. It was the beginning of space and time themselves. There was no before because time itself began with the Big Bang. Asking what happened before is like asking what is north of the North Pole. The question seems meaningful, seems like it should have an answer, but it does not. Yet physicists have proposed models that attempt to make sense of the pre-Big Bang era, that try to give meaning to the question of what came before. One of the most elegant is the Hartley-Hawking no-boundary proposal, developed by James Hartle and Stephen Hawking in the 1980s. This model uses a mathematical technique that converts time into a kind of space by using what is called imaginary time, a mathematical construct in which time is multiplied by the square root of -1. In imaginary time, something remarkable happens. As you trace the history of the universe backward toward the Big Bang, time does not end at a sharp singularity, a point where everything breaks down. Instead, it smoothly curves and closes off like the bottom of a bowl or the south pole of a globe. If you walk south on Earth and reach the South Pole, you can keep walking, but every direction from there is north. There is no point beyond the pole. Similarly, in the Hartley-Hawking model, there is no moment before the Big Bang because time rounds off smoothly at the beginning. In this picture, the universe has no boundary in time. It is finite but unbounded, just as the surface of a sphere is finite but has no edge. There was no first moment, no instant of creation, no singularity from which everything emerged. The universe simply is, complete in itself, requiring no external cause, no creator, no something before it. Hawking famously asked, in this scenario, where is the place for a creator? If the universe has no boundary, no beginning in the usual sense, then it needs no cause, no explanation beyond itself. The universe would simply be a self-contained, self-explaining entity. The question, why does the universe exist, would have no answer, because the universe does not need an external reason for being. Other models take a different approach to the question of cosmic origins. Cyclic cosmologies propose that the Big Bang was not the absolute beginning, but a transition between cosmic eras, a moment of transformation in an eternal cycle. In Roger Penrose's conformal cyclic cosmology, the universe passes through infinite cycles called aeons. Each aeon begins with a Big Bang-like event and ends with an infinitely expanded, cold, empty cosmos. But in Penrose's model, this ending is mathematically equivalent to a new beginning. The key insight is something called conformal invariance. When the universe becomes infinitely large and devoid of massive particles, when all matter has decayed and only massless particles like photons remain, size loses its meaning. An infinitely large, empty universe looks mathematically identical to an infinitely small, hot, dense one. The geometry is the same. The death of one aeon is the birth of the next, and the cycle repeats forever. Penrose has claimed to find evidence for this model in the cosmic microwave background, in the form of concentric circles or anomalously hot spots that might be remnants of supermassive black hole evaporations from the previous aeon. These claims remain controversial, with most cosmologists skeptical that the statistical evidence is strong enough to support such extraordinary conclusions. But the model illustrates how time might not have a beginning in the usual sense, how the universe might be eternal, cycling through endless aeons without ultimate origin or end. The ekpyrotic and cyclic models proposed by Steinhardt and Turok offer another vision of eternal time. In these scenarios, the Big Bang was a collision between branes, and the universe oscillates through endless cycles of expansion and contraction. Time stretches infinitely into the past and future, with no ultimate beginning or end. Each Big Bang is followed eventually by another Big Bang, and there was always a previous cycle before this one. There is also the deeper question of whether time itself is fundamental or emergent. In some approaches to quantum gravity, particularly loop quantum gravity and certain interpretations of the holographic principle, time as we experience it may not exist at the most fundamental level. It may emerge from deeper, timeless physics, the way temperature emerges from the random motion of atoms. At the level of individual atoms, there is no temperature, just particles moving. temperature is a statistical property that emerges from the collective behavior of many particles. Similarly, time might be a meaningful concept for our macroscopic universe, but at the Planck scale, where quantum gravity dominates, time might dissolve into something more fundamental, something we do not have everyday words for. This has profound implications for the edge of the universe. If time is emergent, then the boundary of time is not a wall or a moment, but a transition, a place where our familiar concepts break down, and something else, perhaps something indescribable, takes over. The question, what happened before the Big Bang, might be asking about something that only exists approximately at large scales when the universe is big enough and cool enough for time to make sense. Some physicists have even proposed that the flow of time, the sensation that time passes from past to future, is an illusion. In the block universe model, sometimes called eternalism, past, present, and future all exist equally. They are all real, all there, spread out like a landscape. What we experience as the passage of time is merely our perspective moving through a static four-dimensional structure. If this is true, then the beginning and end of the universe are not events that happen. They simply are, eternal facets of a timeless whole. What lies beyond the temporal edge of the universe? Perhaps nothing, in the sense that beyond is a concept that requires time to have meaning, and there is no time past the edge. Perhaps infinite cycles stretching backward and forward forever, an eternal cosmic heartbeat. Perhaps a timeless realm from which time itself emerges as an approximation. Or perhaps a question that cannot be asked, because the asking requires the very thing whose absence we are trying to contemplate. The edge of the universe is not a wall in space. It is the horizon of time itself, and beyond that horizon lies either the infinite past, a timeless eternity, or a mystery so deep that our concepts of before and after simply do not apply. If the universe is infinite, or if the multiverse is real, then somewhere out there, beyond the edge of what we can see, there may be minds. Not human minds, perhaps not minds like anything we can imagine, but conscious observers, entities that think, perceive, wonder, and question their own existence. The question of intelligence beyond our universe is one of the most profound and unsettling in all of cosmology. Let us start with the sheer mathematics of infinity. If the universe extends infinitely beyond our cosmic horizon, and if the laws of physics are the same everywhere, then the same processes that produced us must be occurring elsewhere. Stars form from collapsing clouds of hydrogen. Planets coalesce from the debris around young stars. Chemistry generates complexity, carbon atoms linking into chains and rings. Eventually, through some combination of chance and necessity, life emerges. In an infinite universe, anything that can happen will happen, and will happen infinitely many times. This leads to a staggering conclusion. If the universe is infinite, there are other versions of you out there, not just similar beings on similar planets, but exact duplicates, atoms arranged identically, neurons firing in the same patterns, living through the same experiences you are living through right now. Physicist Max Tegmark has calculated that the nearest identical copy of you would be about 10 to the power of 10 to the power of 29 meters away. An incomprehensibly vast distance, far beyond anything we could ever travel to or communicate with, but in an infinite universe, a mathematical certainty. This sounds absurd, and perhaps it is. Perhaps the universe is not infinite. Perhaps there are subtle variations in the laws of physics that prevent exact copies from forming. But if the simplest cosmological models are correct, If space extends forever and the same rules apply everywhere, then the conclusion follows inexorably. Infinity is stranger than we can easily grasp. But now, consider a stranger possibility still, one that has troubled cosmologists for decades. What if most of the conscious observers in the universe are not products of evolution at all? What if they are random fluctuations, statistical accidents, minds that pop into existence from the quantum foam and vanish moments later? This is the Boltzmann brain problem, named after the 19th century physicist Ludwig Boltzmann, who grappled with deep questions about entropy and the arrow of time. Boltzmann was trying to explain why the universe appears to be in a low entropy state, far from the thermodynamic equilibrium that physics seems to predict as the natural state of things. He proposed that our ordered universe might be a random fluctuation in an otherwise chaotic cosmos, a pocket of improbable order in a sea of disorder. But this reasoning leads to a troubling conclusion. Random fluctuations are more likely to produce small ordered regions than large ones. It is easier to roll 5 sixes in a row than to roll 1,000,000 sixes. A single brain, complete with false memories of a full life, an entire illusory history implanted by chance, is vastly more probable than an entire universe of genuine complexity with billions of years of real history. If the universe is eternal, or if it extends infinitely in space, then Boltzmann brains should vastly outnumber normal observers like us. These disembodied minds would flicker into existence, experience a single moment of consciousness filled with false memories of a past that never happened, and then dissolve back into chaos. They would think they had lived full lives. They would remember childhoods, friendships, loves, losses. But none of it would be real. The memories would be random arrangements of neurons that happen to encode coherent-seeming stories. If you are a random observer in such a universe, you are overwhelmingly likely to be a Boltzmann brain rather than a being with a genuine evolutionary history. Your memories of reading this script, of your entire life up to this moment, would be illusions. The universe you think you see would be a momentary hallucination. Most cosmologists consider this a reductio ad absurdum, a sign that something is wrong with the reasoning that led to it. If a cosmological model predicts that Boltzmann brains dominate, that most observers are random fluctuations rather than evolved beings, it is probably a bad model. This has led to constraints on acceptable theories. A good theory should not predict that we are Boltzmann brains, that our memories are false, that our perception of an ordered universe is an illusion. Sean Carroll and other physicists have argued that the Boltzmann brain problem points to something important about the nature of the vacuum and the arrow of time. Perhaps the universe is not eternal. Perhaps there is something special about the initial conditions that prevents the proliferation of random observers. Perhaps our understanding of quantum mechanics and cosmology is missing something crucial. The problem remains unsolved, but it highlights how questions about intelligence beyond our universe can constrain fundamental physics itself. Now consider an even more radical possibility, the simulation hypothesis. Philosopher Nick Bostrom argued in a famous 2003 paper that if advanced civilizations can create realistic simulations of conscious beings, they probably will, and they probably will create many such simulations. Running ancestor simulations, recreating the lives of beings who lived in earlier eras, might be a common activity for technologically mature civilizations. If so, then simulated beings would vastly outnumber real ones. Think about it this way. If humanity survives and continues to advance technologically, we might eventually have the computing power to simulate entire worlds, complete with conscious inhabitants who do not know they are simulated. These simulated beings would think they are real. They would look up at their simulated sky and wonder about their simulated universe. And there might be vastly more of them than there are real beings in the base-level reality. If this is true, then any randomly chosen conscious entity is more likely to be simulated than genuine. Could our universe be a simulation running on a computer in some higher reality? Could the minds beyond our cosmic edge include not just aliens and Boltzmann brains, but the simulators themselves, beings in a parent universe who have created our reality as an experiment, an artwork, a game, or a project we cannot fathom? The simulation hypothesis is difficult to test, perhaps impossible. How would you detect the walls of your simulation from inside it? But it raises profound questions. If we are simulated, then the edge of our universe might be the edge of the simulation, a boundary beyond which the code does not extend. The laws of physics might be algorithms. The fundamental constants might be parameters in a program, and the beings who created us might be watching, intervening, or simply letting the simulation run. There is also the idea of cosmic natural selection, proposed by physicist Lee Smolin in the 1990s. In this scenario, black holes give birth to new universes, and each daughter universe has slightly different physical constants from its parent. Universes that produce many black holes have many offspring, and over countless generations, universes evolve to be good at producing black holes. Since the conditions that favor black hole formation also favor star formation, chemistry, and life, this process might explain why our universe is hospitable to intelligence. Smolin's idea makes testable predictions. If cosmic natural selection is correct, our universe should be near optimal for producing black holes. Any small change in the fundamental constants should make fewer black holes, not more. This prediction can be checked against observations and simulations of how physics would work with different constants. So far, the idea remains intriguing, but unproven. But Smolin's idea raises a further possibility. What if intelligence itself plays a role in cosmic reproduction? What if advanced civilizations learn to create black holes deliberately, or to spawn new universes through other means? In this case, intelligence would become a force in cosmology, shaping the evolution of the multiverse. Universes that produce intelligent life, capable of creating more universes, would have more descendants than universes that do not. Over cosmic time, the multiverse would come to be dominated by universes friendly to intelligence. Some thinkers have gone even further, proposing that consciousness is fundamental to the universe, not a byproduct of physics, but a basic feature of reality. In these panpsychist models, mind is everywhere, not just in brains, but in atoms, in fields, in the fabric of space itself. If this is true, then the question is not whether there is intelligence beyond our universe, but whether the universe itself, in some sense, is intelligent. Could we ever communicate with minds beyond our cosmic horizon? In standard physics, the answer is no. The expansion of the universe ensures that we are causally disconnected from regions beyond a certain distance. No signal can reach us from there, and no signal we send can reach them. Even if there are trillions of civilizations beyond the edge, we will never receive their transmissions, never know they exist, never exchange even a single bit of information. But in more speculative scenarios, there might be ways around this limit. If wormholes exist, they could provide shortcuts through space-time, allowing communication across distances that light could never traverse. If extra dimensions allow for signals through the bulk, messages might bypass the usual barriers. If the universe is cyclic, information might persist from one aeon to the next. Penrose has even suggested that intelligent beings in a previous aeon might have encoded messages in gravitational waves that left imprints on our cosmic microwave background, patterns that we could detect today if we knew how to look. We have received no signals from beyond. The silence of the cosmos is profound, but absence of evidence is not evidence of absence. The minds beyond our edge, if they exist, might be too far away, too different, too advanced, or too uninterested to make contact. Or perhaps they are there, and we simply do not know how to listen. The question of intelligence beyond the universe is ultimately a question about the nature of mind, the structure of reality, and our place in the cosmos. Are we alone, not just in our galaxy, but in all of existence? Are we one of countless minds scattered through an infinite multiverse? Are we the dreams of a Boltzmann brain, the characters in a simulation, the thoughts of a cosmic intelligence? We do not know, but the question itself reveals something profound about who we are. Beings who wonder, who ask, who reach beyond the edge of the known into the vast unknown. Whatever lies beyond, that wondering is part of it. How do we study what we cannot see? The edge of the observable universe is defined by light that has traveled for 13.8 billion years. Beyond that edge lies a realm no telescope can reach, no probe can visit, no experiment can directly access. The distances involved are so vast, the timescale so long, that the notion of going there and looking is not merely difficult, but physically impossible. Light itself cannot carry information from those regions to us, and yet science has developed remarkable methods for inferring what lies beyond, for testing theories about the unseen, and for pushing the boundaries of knowledge into territories once thought forever closed. This is one of the great triumphs of human ingenuity. We can know things about places we can never visit. The cosmic microwave background is our deepest probe into the past, and, in a sense, our closest view of the edge. This ancient radiation, released when the universe was just 380,000 years old, carries information about conditions in the early cosmos. By studying its temperature fluctuations, measuring variations of just a few parts in 100,000 across the sky, cosmologists can infer the geometry of space, the total density of matter and energy, and the nature of the quantum fluctuations that seeded the formation of galaxies. The Planck satellite, launched by the European Space Agency in 2009 and operated until 2013, mapped the cosmic microwave background with unprecedented precision. Its measurements confirmed that the universe is geometrically flat to within 0.4%, a result consistent with predictions of inflationary theory. They revealed subtle patterns in the distribution of temperature fluctuations that constrain the physics of inflation, the nature of dark matter, and the possibility of features from beyond our horizon. One tantalizing hint that has attracted much attention is the CMB cold spot, a region in the constellation Eridanus that is significantly colder than the surrounding background, about 70 microkelvin colder than the average. Some physicists have proposed that this anomaly might be a scar from a collision with another universe, a bruise left when our bubble universe brushed against a neighbor during the epoch of inflation. The Eridanus supervoid, a vast underdense region of space, accounts for some of the temperature dip, but not all of it. The evidence is far from conclusive, and most cosmologists consider the anomaly likely to be a statistical fluke, but it illustrates how even the unseen might leave traces in what we can observe. Gravitational waves offer another window into the hidden cosmos. When massive objects accelerate, when black holes spiral together, or neutron stars collide, they create ripples in spacetime that propagate outward at the speed of light. These waves pass through matter almost unimpeded, carrying information from events that light cannot reveal. They are messengers from the gravitational universe, a realm that electromagnetic radiation cannot access. The LIGO and Virgo detectors have already observed gravitational waves from colliding black holes and neutron stars, opening an entirely new field of astronomy. Future detectors, including the space-based LISA mission, planned for launch in the 2030s, will be sensitive to different frequencies, allowing them to detect waves from supermassive black hole mergers and potentially from the early universe itself. Primordial gravitational waves generated during cosmic inflation would provide direct evidence for that epoch and could distinguish between different models of the early universe. The ekpyrotic model predicts very weak primordial gravitational waves, while standard inflation predicts stronger ones. Detecting or ruling out these waves would be a major step in understanding what lies beyond the observable edge. The CMB-S4 experiment and the Simons Observatory are specifically designed to search for the polarization patterns that primordial gravitational waves would imprint on the cosmic microwave background. The search for bubble collision signatures is another frontier in observational cosmology. If eternal inflation is correct and our universe is one of many bubble universes, then collisions between bubbles might have occurred in the distant past. These collisions would leave characteristic patterns in the cosmic microwave background, circular or elliptical regions with anomalous temperature or polarization, distinct from the statistical patterns expected from quantum fluctuations during inflation. Several research groups have searched for such patterns with intriguing but inconclusive results. The search continues with each new dataset, each improved analysis technique. Future experiments promise to push these boundaries even further. The James Webb Space Telescope, launched in 2021, observes the universe in infrared light, revealing galaxies from the earliest epochs of cosmic history. It has already detected galaxies that formed just a few 100 million years after the Big Bang. During the era when the first stars ignited and the universe transitioned from the cosmic dark ages to the era of light. While JWST cannot see beyond the cosmic microwave background, it illuminates the period immediately after, filling in our picture of cosmic history. Ground-based observatories like the Vera Rubin Observatory, set to begin full survey operations soon, will map the entire visible southern sky repeatedly over a decade. It will detect millions of transient events, supernovae, and variable stars and asteroids. It will map the distribution of dark matter through gravitational lensing, measuring how the mass of galaxy clusters bends the light from more distant sources. It will constrain the nature of dark energy by observing how the expansion of the universe has changed over cosmic time. At the smallest scales, particle accelerators probe the conditions of the early universe by recreating, for the briefest instance, the energies that existed fractions of a second after the Big Bang. The Large Hadron Collider at CERN has discovered the Higgs boson, the particle associated with the field that gives mass to other particles. It has searched for supersymmetric particles that might explain dark matter, for signs of extra dimensions, for any deviation from the standard model of particle physics that might point toward new physics. Future colliders, if built, could reach even higher energies, potentially revealing the physics of inflation or the nature of the electroweak phase transition. But there is a limit to what experiments can achieve, a horizon beyond which direct observation may be forever impossible. The Planck scale, the energy scale where quantum effects become important for gravity, lies at roughly 10 to the 19 GeV, about a quadrillion times higher than the energies the LHC can reach. We may never build an accelerator powerful enough to directly probe quantum gravity. The energies required would demand accelerators the size of galaxies or larger. This does not mean we cannot learn about quantum gravity and what it might tell us about the edge of the universe. Indirect methods, mathematical consistency requirements, and theoretical elegance may be our only guides. We can require that candidate theories be internally consistent, that they reproduce known physics in the appropriate limits, that they connect to observations in ways that constrain their structure, even if they cannot be directly tested. This brings us to a fundamental question that has occupied philosophers of science for decades. Are there things that can never be known? Philosopher of science Karl Popper argued that the hallmark of scientific theories is falsifiability, a statement that cannot, even in principle, be tested against evidence is not scientific. By this criterion, some claims about what lies beyond the observable universe may fall outside the domain of science entirely. If the multiverse exists, but is causally disconnected from us, if other universes can never influence anything we observe, then their existence may be permanently unknowable. This does not mean the multiverse is not real. Reality need not confine itself to what we can observe, but it raises profound questions about the nature of scientific knowledge. Can we accept a theory because it is mathematically elegant and emerges naturally from well-tested physics, even if some of its predictions can never be tested? Some physicists, like Leonard Susskind, argue that the multiverse should be taken seriously because it emerges naturally from well-tested theories like inflation and string theory. The same equations that predict phenomena we have observed also predict phenomena we cannot observe. Rejecting the unobservable predictions while accepting the observable ones seems arbitrary. Others, like Sabine Hossenfelder and George Ellis, warn that unfalsifiable claims can lead science astray, that elegance and naturalness are not reliable guides to truth. There is also the question of computational limits. Simulating the entire universe at the quantum level would require a computer larger than the universe itself. Some features of reality may be compressible, describable by simple equations, but others may be irreducibly complex. We may never fully understand the universe because understanding requires a model, and the universe may not fit into any model smaller than itself. Despite these limitations, the history of science is a history of expanding horizons. Things once thought unknowable have yielded to human inquiry. The composition of stars, once thought forever inaccessible, was revealed by spectroscopy. The age of the universe, once a matter of pure speculation, is now measured to percent-level precision. The structure of the atom, invisible to the naked eye, is mapped in exquisite detail. Perhaps the nature of what lies beyond the edge will similarly yield, through methods and insights we cannot yet imagine. What we can say is that the quest continues. Every generation has pushed the boundaries of the known, revealing more of the cosmos than the previous generation thought possible. The edge of the universe is both a boundary and a challenge, a limit and an invitation. And as long as there are minds that wonder, the exploration will not end. We have traveled far in this journey, from the edge of the observable universe to the speculative shores of the multiverse, from the seething quantum foam of the vacuum to the silent boundaries of time itself. We have explored brains floating in higher dimensions, bubbles nucleating in false vacuum, minds flickering into existence from random fluctuations, and universes colliding in the dark. And now, at the end, we return to the question that started it all. What exists outside the edge of the universe? The honest answer is that we do not know. but we have learned something profound about the shape of our ignorance, about the contours of the unknown, about the many forms that beyond might take. One possibility is that beyond the edge lies simply more universe. The cosmos extends, perhaps infinitely, in every direction, filled with galaxies and stars and planets much like our own, governed by the same laws of physics, shaped by the same fundamental constants. In this picture, the edge is an artifact of our limited perspective, a horizon defined by how far light has traveled since the Big Bang, not a real boundary in space. There is no wall, no discontinuity, no end to the story. Just an endless continuation of everything we see around us. If this is true, then somewhere out there, beyond any distance we can name, there are other versions of everything. Other Earths, other civilizations, other beings pondering the same questions we ponder. The universe would be not just big, but infinite, containing every possibility, every variation, every story that could be told. Our lives, our world, our entire cosmic neighborhood would be replicated countless times across an endless expanse, an infinite library containing every possible book. Another possibility is that beyond the edge lies other universes, realities fundamentally different from our own. The multiverse, in one form or another, might be real. Bubble universes spawned by eternal inflation, each with its own physical constants, its own particle zoo, perhaps its own version of chemistry and life. Brain worlds floating in higher dimensional bulk, close to us in dimensions we cannot access, forever unreachable. Branching timelines of quantum mechanics, where every possibility is realized and every choice spawns new worlds. If the multiverse exists, then our universe is not alone. It is one island in an archipelago of realities, one bubble in an endless foam, one sheet in an infinite stack. What lies beyond our edge is not more of the same, but something different, perhaps unimaginably different, governed by other laws, shaped by other histories, containing other forms of existence we have no capacity to comprehend. A third possibility is that beyond the edge lies nothing, true nothingness, the absence of space and time and matter and even potential. Not a void, not an emptiness, but non-existence itself. In this picture, the universe is finite, bounded, complete. There is no beyond because beyond requires space in which to exist, and there is no space past the edge. The universe would be like the surface of a sphere, finite but unbounded, with no edge you can point to but nowhere to go if you could travel forever. Or perhaps the question itself is confused, based on assumptions that do not hold at the deepest level. Beyond implies a direction, a there rather than here, a something past something else. But if space and time are properties of the universe rather than containers it exists within, then asking what lies beyond the universe may be asking about something that cannot exist. The universe may not have an outside any more than the number 7 has a smell, or Tuesday has a weight. The concepts simply do not apply. What is certain is that the question humbles us. We are small creatures on a small planet orbiting an ordinary star in the suburbs of a typical galaxy among hundreds of billions of galaxies in the observable universe. The observable universe contains at least 200 billion trillion stars, a number so large it has no meaning to the human intuition. And the observable universe may be an infinitesimal fraction of what exists. Our lives are brief flickers in cosmic time, our world a mote in the vastness. Our knowledge, hard won over millennia of effort and genius, barely scratches the surface of what there is to know. And yet we ask. We build telescopes that gather light that has traveled for billions of years. We construct particle accelerators that recreate conditions from the first fraction of a second after the Big Bang. We send probes to distant planets and moons. We develop theories of unimaginable abstraction and test them against the faintest whispers of ancient light. We are the universe becoming aware of itself, matter contemplating its own existence, complexity questioning its own origins. There is something magnificent in this, not in having answers but in asking questions, not in knowing but in seeking. The edge of the universe is a boundary, yes, but it is also an invitation. It calls us to wonder, to explore, to imagine. It reminds us that no matter how much we learn, there will always be more to discover. The frontier is infinite, and the exploring will never end. Perhaps one day we will understand what lies beyond. Perhaps we will find evidence for the multiverse, signals from other brains, patterns from previous aeons. Perhaps we will develop a theory of quantum gravity that dissolves the mystery of the Big Bang, showing us what happened before time began, or why beginning is the wrong concept entirely. Perhaps we will create simulations of our own, becoming the creators of digital universes, and in doing so understand what it might mean for us to be simulated ourselves. Or perhaps we will reach the limits of what can be known. Perhaps some questions are unanswerable, not because we lack the intelligence or technology, but because the universe simply does not contain the information needed to answer them. Perhaps we will learn to be at peace with mystery, to find meaning not in certainty, but in the quest itself. Whatever lies beyond the edge, it has shaped us. The vastness of the cosmos, the strangeness of quantum reality, the deep time of cosmology. These are not just facts about the world. They are the context of our existence, the stage on which our lives unfold. We are made of star stuff, as Carl Sagan said, atoms forged in the hearts of ancient stars. And that star stuff has become conscious and curious. The universe, through us, is asking questions about itself. The edge of the universe is not just a boundary in space or time. It is a boundary of understanding, a frontier of knowledge, a challenge to the human spirit. And that frontier is always receding, always revealing new mysteries, always calling us forward. So let us end not with an answer, but with an attitude, wonder, curiosity, humility. The universe is vast beyond comprehension, and our understanding of it is a candle in an infinite dark. But what a candle it is! What a privilege to be the ones who ask, who seek, who wonder. What exists outside the edge of the universe? We may never know. But in asking the question, we become part of the answer. We are how the universe explores itself, how existence contemplates its own nature, how the cosmos reaches toward its own edge. And that, perhaps, is enough.